All right. Hello, everyone. Can you guys hear me now? Welcome to the first public science lecture series at on our FIT Astro YouTube channel. Apologies for all the technical difficulties we're having. We had to set up a different uh, device. So thank you again for your patience and for sticking with us. So today we have Dr. Manasvi Lingam from the Florida Institute of Technology, who is a professor of astrobiology here at Florida Tech. And today we're going to learn about this new and exciting field of astrobiology. So, all right, great. Thank you guys for your feedback. And here we go this time. Dr. Lingam, take it away.
All right. So, oh. All right. So, I assume you can all see the slides here. Oops. Oh dear. Just a second. All right. Apologies for the error. So here, okay. So let's get started. So as my title says, the emerging science of astrobiology. Now we are all aware of what the sciences entail. We all know of physics, chemistry, biology, um, astronomy, and so on. It's very rare, however, that one gets to be born and to live in an era where you see a new field emerging, maturing, and growing. And that field, which I will be talking about today, is none other than astrobiology. So we must, of course, ask ourselves, what is astrobiology? And the answer is best found by looking to the NASA Astrobiology Institute. And so let me just read it out. Astrobiology is the study of the origins, evolution, distribution, and future of life in the universe. This interdisciplinary field requires a comprehensive, integrated understanding of biological, geological, planetary, and cosmic phenomena. As the name indicates, and this definition indicates, astrobiology is a multidisciplinary field that synthesizes elements of physics, astronomy, chemistry, geology, biology, and many more. With, and then we can ask ourselves, what is the scope of astrobiology? As indicated by the previous slide, the scope of astrobiology includes not just the origin and evolution of life on our planet, namely planet Earth, but also looking at how the habitability of other worlds is governed. Mars, of course, is a very well-known example, and the icy worlds, as they're called, namely the icy moons of Saturn and Jupiter, such as Europa, also fall under the umbrella of astrobiology. And last but not least, we have the rapidly growing field of exoplanets and searching for life on them. And this defines the scope of astrobiology. Now we must ask ourselves, what are the questions that this field seeks to grapple with? And there are three fundamental questions in all, which are as follows. The first is, where did we come from? Which, in a slightly more scientific language, would be cast into how does life begin and evolve. The second is perhaps the most famous of the trio, and it is, are we alone in the universe? Does life exist elsewhere in the universe apart from Earth? And third, where are we going? So, what is the future of life on our planet as well as on other worlds? And as I said before in my very start of the talk, that astrobiology is a new field which is in the process of maturation. But although it is a new field, it is one which has long and deep roots. Nearly 2,500 years ago, the Greek philosopher Metrodorus of Chios stated, it would be strange if a single ear of wheat grew in a large plain, or there were only one world in the infinite. So even back then, people were speculating about the plurality of worlds in the cosmos and the notion that one might have life inhabiting some of them. And over the centuries and millennia, many other thinkers speculated about this topic, but it's only in the 1950s and 1960s that the birth of exobiology saw it saw it happen. So exobiology is a subfield of astrobiology, which primarily focuses on the second question we saw earlier, namely, are we alone? So it primarily focuses on extraterrestrial life. And one of the founding uh, people in this field was the Nobel laureate Joshua Lederberg, who you see in the picture here. And he was at the forefront of US efforts in exobiology in the 20th century. And this particular image is taken from him working in his laboratory at the University of Wisconsin in 1958. And so, what we are going to do now is we are going to take a voyage through space and time, covering many worlds and many eons in the process. And this journey will be organized along the lines of the three questions that astrobiology seeks to answer. First, of course, we will look at how did life originate and evolve. And because this field is a new field that is growing rapidly and maturing rapidly, I have decided here to only focus on the accomplishment from the last 5 years. And you will see, even in the last 5 years, there's a great deal that we have learned about many of the aspects underpinning astrobiology. So, the first thing, in order to understand how the origin of life transpired, one must seek to understand how the components that make up a living organism, which are biomolecules, actually came to be. How did the various ingredients of a living cell come to be? It turns out there's four major classes of biomolecules. First, we have the lipids, which form the boundary of the cell membrane. And then we have the nucleic acids, DNA and RNA, which don't really need an introduction. And then we have carbohydrates, which of course we are all familiar with as energy sources in food. And then last but not least, we have proteins, which play a very wide variety of roles in the cell, ranging from providing structural stability to acting as catalysts in the form of enzymes. And therefore, we must ask ourselves, how could these rather complex molecules have been synthesized from fairly simple ones? And this field too has deep roots, and one of the most famous among them are the so-called Miller-Yuri experiments, which took place in 1952, 1953. So what Stanley Miller, who was a graduate student at that time, did was it took a mixture of gases, which are shown in this figure here, gases which were believed to have existed on the early Earth in large abundance, such as water, methane, ammonia, and hydrogen. And then he put a pair of electrodes in this flask that you see, and then he periodically sent electric sparks through this particular flask, which simulated lightning. And this was the setup. And finally, the products were condensed, and then they were collected, and then they were sampled and probed. And what was found was that even though one started with these very simple gases, which were believed to have been common back then in the early Earth, it turned out that a lot of very complex molecules were formed, including a minimum of 5 amino acids, which are the building blocks of protein that we encountered earlier. Since the Miller-Urey experiment, literally thousands of papers have been written on this subject, and I will just show you one example out of many that exist. Now, you will look at this figure, and no doubt, it just seems incredibly complex, which of course it is. And I obviously don't expect anyone to focus on all the details. There's only three major takeaways that need to be taken away from this figure. First, it turns out that in 2015, Patel et al. Came up with this particular way of synthesizing all the four building blocks of life that we saw earlier on: lipids, carbohydrates, proteins, and nucleic acids. They found ways to synthesize the building blocks of all these molecules by starting from a common set of similar molecules that are believed to be universally common on Earth. So that's the first major takeaway. The second is this particular pathway required ultraviolet radiation as the energy source to kickstart the whole process of, this chemical reaction. And thirdly, the molecules that were involved were the molecule hydrogen cyanide, which is where my cursor is, and also the molecules, and then it also involved hydrogen sulfide and or sulfur dioxide. So the presence of hydrogen cyanide explains why the cyano comes into picture here. So it's called cyanosulfidic metabolism. And the cyano comes from the hydrogen cyanide, and the sulfide comes from the fact that hydrogen sulfide was used. But that's just one example of the progress that chemists have made in synthesizing these building blocks of life. And the next question we must ask ourselves is, where did this origin of life occur? And before we get to that, I just want to mention that the Earth consists of a vast array of environments, many of which are connected to one another. And on the early Earth, there would have been a multitude of processes that would have been occurring. Processes such as the circulation of the oceans, the circulation in the atmosphere, impacts from asteroids and comets, which would have been occurring a lot more frequently than now. The moon, which was a lot closer to the Earth, would have exerted much stronger tides. There would have been volcanic activity and so on. So many of the various environments of Earth, even though they were functioning independently, they were actually all connected to one another through these various modes of circulation, and they were all interacting with one another. Therefore, it's more appropriate to view the Earth as a global chemical reactor, as suggested by Eva Stukin and her colleagues in 2013. And so now, as I said, we don't quite know where life might have originated. One of the most promising contenders are the hydrothermal vent, which can be envisioned as being the analog of geysers and hot springs, but instead of being on the surface, they're situated at the bottom of the ocean. So they're essentially cracks on the Earth's surface where you have heat welling up and heated water that is being processed in that particular region. Some people have argued that the hydrothermal vent can be visualized as the plumbing for Earth's ocean. And these particular sites are believed to have been quite promising for the origin of life in multiple respects. So we've looked at what kind of processes that could have led to complex molecules. We've looked at one environment. And then the next question is, when when do the first signs of life appear on Earth? And here too, there has been a lot of work done on this front. For instance, in Quebec, rocks that date from 3.8 to 4.2 billion years ago old were found to have these filamentous structures along the lines that you see in this diagram here. And these filamentous structures turn out to be very similar to those that are produced by microbes dwelling in hydrothermal vents. And moreover, these particular structures were recovered from ancient hydrothermal vents, which, as we saw in the previous slide, could have been one of the primary sites for the origin of life. So there's some tantalizing evidence that these filamentous structures that one finds, for instance seen here, could be indicative of the remains of fossilized microbes. And this particular belt of rocks dates from 3.8 to 4.2 billion years old. And then moving on, if one moves all the way from Greenland, which is where we were, to Western Australia, and I apologize for the typo, it should just be Western Australia. Um, we go to a place called Jack Hills, and in the Jack Hills, there was these particular minerals known as zircons, which were recovered. And these zircons are quite remarkable because they represent some of the oldest material known on Earth. And these particular zircons are really hardy, and hence they have survived over the billions of years. And by analyzing these zircons, one can look at how much carbon is present in them, and moreover, what amounts of the isotopes of carbon are present in them. So, isotopes of a given element are the same element but of different masses. And it turns out that biology gives rise to different ratios of these isotopes as compared to non-biological processes. And in 2015, Elizabeth Bell et al. Found evidence that these isotope ratios could have been compatible with those associated with modern biology today. And this particular crystal that was analyzed, the zircon crystal, was about 4.1 billion years old. And then a third line of evidence that I want to mention comes from, oh, I apologize. So I forgot to say that this was from Australia. The first one was from Quebec. I mistakenly said Greenland before. And now we come to Greenland. And this is the Ishwar Greenstone belt. And this represents another line of evidence. So you see this particular dome-like structure that appear in here. And moreover, we can see that there's darker regions on the top and lighter regions in the bottom. And these particular structures are sedimentary structures, and they're essentially formed by the action of microbes, which gather bits of sediment, and then they secrete compounds that allow them to accrete these particular sediment and form these large-scale structures. So when you have microbial communities that live, these kind of structures are produced. And these structures are known as stromatolites, and they're also believed to be promising signs for the evidence of life. So that's one more line of evidence. And these particular rocks that you see here are from 3.7 billion years old. So in the first case, when we looked at the rock from Quebec, the tantalizing evidence from there was between 3.8 to 4.2 billion years old. The evidence from Australia, coming from a different avenue, is about 4.1 billion years old. And thirdly, this evidence from Greenland is about 3.7 billion years old. So all in all, there is a fairly, scientists agree that there's fairly good evidence that life was present on Earth by 3.7 billion years ago, and perhaps even earlier. It's just that the deeper that we go into time, especially once we cross the 4 billion year ago mark, it turns out that the amount of preserved material we have from back then is really low, as a result of which it's hard to definitively identify signs of life from that period. And so this completes the brief overview of, where, how did life originate and evolve, where did we come from, and so on. The bulk of my discussion will focus on the second question, namely, are we alone? And so there's quite a few worlds that fall under the cat. So there's quite a few targets that we could look at, because are we alone essentially implies the question of trying to find whether there is extraterrestrial life in the universe. And so there are a number of targets we could look at, and to spend time on all of them would take hours. So I'll just be going through a few of them. So first, let's look at Venus. Venus, at first glimpse, seems to be a very inhospitable and hostile world. It has a surface temperature of more than 850 Fahrenheit. Its atmospheric pressure at the surface is about 90 times that of the Earth. So at first sight, one might say, well, Venus doesn't seem very promising. But more than 50 years ago, Harold Morowitz and Carl Sagan, the latter of whom I'm sure many of you would would recognize, suggested that if you go high enough into Venus' atmosphere, the temperatures drop, the pressure also drops, and you end up with this region about 50 kilometers above the surface, where both the temperature and the pressure are quite conducive to life. And this field received a big impetus last year when a particular gas was detected in the atmosphere of Venus. And this gas is known as phosphine, which has the chemical formula PH3. So it consists of phosphorus and hydrogen. And why was this particular discovery seen as such a milestone? And the answer is that phosphine, at least on Earth, is largely produced by anaerobic bacteria. That is to say, bacteria that survive in the absence of oxygen. And so it's the fact that phosphine was detected, reportedly detected in the atmosphere of Venus, sparked a lot of interest that perhaps it could harbor life. So subsequent studies there's been a lot of debate about whether the phosphine was actually detected, whether it could have been a different gas. And there's also been a lot of debate about whether, if the phosphine does exist, whether it has a biological origin or whether there is some kind of a natural process, a geological process, for instance, that is producing this phosphine. So there's been a lot of debate on this front in the scientific community over the past year or so. And so, if we want to settle the debate, how could we do that? Now, just by taking data from Earth, it turns out that a lot of the debate about whether the phosphine signal is genuine or not comes from the fact that we were using telescopes and we were operating them at the very threshold of their sensitivity. So, therefore, it would suggest that if we really want to go and look for life in the clouds of Venus, the best way is actually to go there and then to study them right there. And so, with with a mixture of scientists and engineers, including myself, we looked at this particular scenario in more detail. And what we did was we took advantage of the great progress made in the miniaturization of scientific instruments, such as mass spectrometers, microscopes, and so on. And we also took advantage of the rapid miniaturization of spacecraft to come up with what we call the Precursor astrobiology mission, which is a low-cost, lightweight mission that can go there, perform some basic experiments without entailing too much cost, that could serve as the forerunner for more detailed missions in the future. And our idea was to deploy a bunch of to deploy a spacecraft that would enter the Venusian atmosphere, deploy a parachute, slow down, and once it reaches near the cloud layer, there would be a bunch of probes that would be launched from it. And these probes would stay aloft in the Venusian atmosphere by the use of balloons, which are shown here. And at the very bottom, you see the probe here. And so this particular mission would be able to search for signs of life through 2 or 3 different channels, which I won't get into here. But this is the basic principle that it would operate on, namely the utilization of balloons in the Venusian atmosphere. And then we come to Mars, which of course we all know about. We see it in the sky every day, and likewise with Venus. Now, Mars is also a fairly inhospitable place. Its temperature is about minus 80 Fahrenheit, although there are significant fluctuations either way, both higher and lower. Moreover, the atmosphere of Mars is very thin, so the surface is continuously being bombarded by ultraviolet radiation and by high energy particles from the sun as well as from the rest of the galaxy. So there are many impediments to habitability that exist, but if you were to go below the surface of Mars, 2 things would happen. Firstly, if you go deep enough, most of that radiation that hits the surface would no longer be a factor, and therefore life could be protected there. Secondly, the more deeper you go, the hotter the temperature becomes. And so, if you go deep enough, there will be a zone underneath the surface of Mars where the temperatures will be conducive for the existence of liquid water, which exists between 32 Fahrenheit and 212 Fahrenheit at the surface of Earth. And you will also have temperatures that are conducive to living organisms. So in some work, what we did was we tried to look at what the thickness of this subsurface, this subterranean region could be, where the right habitable conditions exist. In other words, the right temperatures for life. And our model basically looked at a number of worlds, including Mars, but also uh, planets and moons, both within the solar system and outside it as well. And what we find, for instance, in the case of Mars, is that you may have a region ranging from 5 kilometers below the surface or so to all the way until 15 kilometers below the surface, where you could have the right conditions for life. In other words, because the temperature would be conducive to the existence of liquid water, you could have liquid water and the right temperatures in that region. And it turns out the first detection of subsurface water, so water below the surface, happened through the Mars Express spacecraft of the European Space Agency in 2018. Now, that particular detection was also debated to some degree, but there was subsequent data that came out, some of which just came out a week or so after we had published a paper, which showed the existence of more and more water bodies underneath the surface. And these water bodies were detected through the use of radar. So it's been confirmed that there are subsurface water bodies on Mars, and life on Earth, of course, requires water as a prerequisite. And so where there is water, there is the possibility of life as we know it. And perhaps with the Perseverance rover, currently traversing the surface of Mars, it is the next few years promise to be very interesting. And perhaps in the most best case scenario, the Perseverance rover might find either extant or currently extant life. And the third world that I want to take you to is Titan, which is the moon of Saturn. And it is a very unique moon. It's a large moon. It is the second largest in the solar system. It is and it is not that far removed from the size of Mars. In fact, it is a bit smaller than Mars, but not by a whole lot. And Titan is very cold because it orbits Saturn, and Saturn is very far away from the sun. So the temperature of Titan is minus 290 Fahrenheit. Um, and so Titan is a pretty complex world because it has many layers. At the top layer, the topmost layer, consists of an atmosphere which is very rich in all kinds of organic molecules, as well as a surface consisting of a very rich terrain, rich geological terrain consisting of hills and valleys, lakes and seas, which also consists of many different organic molecules. And then if one goes a little bit below, one has an icy layer underneath that. And if one goes even more below that icy layer, there's this subsurface ocean of liquid water that exists deep below the surface. We don't know at the exact location, but we believe that it is 100 or 200 meters, 100 or 200 kilometers below the surface. And this icy ocean is sandwiched between two ice layers. And finally, in the very interior, one has the core and so on. So as I said, Titan is a very unusual moon because it has an atmosphere, it has liquid on the surface as well as deep underneath the surface. Now, the liquid that is present deep underneath the surface is liquid water, but the liquid that is present on the surface is a mixture of hydrocarbons, mostly methane and ethane. And here we see an artist's rendition of how a hydrocarbon lake on Titan would look like, consisting mostly of methane and ethane, the two of the simplest hydrocarbons that exist. And now I said before that life on Earth requires water. So as the solvent, uh, and if we were to, if there was going to be life on Titan, it would have to be very different from that of Earth because the solvent would be quite different. And so therefore Titan is believed to be one of the best abodes for finding life that is exotic in the sense that it is different from life on Earth. The cold temperatures that one has, the very different solvent that one has, and so on, would make life potentially very different from that which we find on Earth. And so, if we have a fusion mission that is going there, we need to understand some of the properties of this hypothetical life that could exist. Because if you are going to look for life, you need to have some idea of what you're looking for. For instance, you might need to know what the sizes of the microbial organisms could be, what the minimum sizes could be, and so on. And there's because of the fact that Titan is so radically different from Earth in several respects, such as in its temperature, such as the fact that instead of having liquid um, oceans of liquid water, it has lakes and seas of liquid methane and ethane. Because of all these differences, there's not been much work done on the subject. Recently, I tried to look at under what condition would a microbe be able to sense information effectively from its environment, because a lot of life is based on information processing. So we acquire, it's not just humans, also microbes do it. They acquire information from the environment through multiple ways. For example, it could be variations in light, it could be variations in temperature, it could be variations in the concentrations of cells. And so they learn about the environment and they react accordingly. So some of the work that I've done tries to see under what kind of a minimum cell size one would need in order for this information processing to occur effectively. And it turns out that ideally you want to be above this threshold, which is known as the signal to noise ratio. And this essentially tells us under what conditions can cells detect information about their environment in an effective manner. And that if so, in other words, you have to be above this threshold, and there's many different modes by which organisms can sense information about their environment. So that's why you have a number of different curves here. But the point is, we can see that a lot of these curves cross the horizontal line at around a few tenths of a micron. So a micron is 1 millionth of a meter or 1,000th of a millimeter. And we find that in many of the cases, the cells have to be at least a fraction of a micron. So they have to range between zero point 0.1 and zero point 0.5 micron. That's between between zero point 0.1 and 1 micron, and in many cases between zero point 0.1 and 0.5 microns to be effective at this information sensing. And so far, and of course, the predictions that were generated from the model can be tested by future mission. And there is one such mission that is in the offing, which is being currently planned, designed, and built. And that is none other than the Dragonfly mission to Titan, which relies on using a rotorcraft, something like a helicopter, to traverse the surface of Titan and to carry out various experiments along the way to look for signs of life and also to understand the habitability of Titan's environment. And this mission is expected to launch in 2027, and it will reach Titan in about 10 years thereafter. And so we've looked so far at targets within the solar system. Now we are going to go outside the solar system. And in particular, we are going to venture into the realm of exoplanets. And in 2019, the Nobel Prize uh, in physics was given to two astronomers for detecting the first exoplanet around a sun-like star. And here are the two scientists that you can see right here. So the field of exoplanets has grown tremendously. We detected this particular exoplanet that these two authors did in 1995. And of course, then we had one exoplanet. And now we have a total of uh, nearly 5,000 exoplanets, and the number rapidly continues to increase. And so the first concept that I want to talk about is something called the habitable zone. So we said earlier that water is one of the prerequisites for life as we know it. So uh, if we want to look for exoplanets that are interesting, there's a lot of emphasis on trying to find exoplanets where the temperatures on the surface would be conducive for the existence of liquid water. Now, the fact that the temperatures are conducive doesn't automatically mean that one would have water on the surface, but it does at least provide us a starting point to get going. And so that particular region around the star where the temperatures are conducive for the existence of liquid water is known as the habitable zone. And we found many planets that fall in the habitable zone. In our own solar system, we have the Earth, which is not a surprise. The blue shaded region is the habitable zone. And then there's Proxima Centauri b, which is the closest exoplanet to Earth, and that also lies in the habitable zone. And and then we have three planets here, which are TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g. So what are these TRAPPIST-1 planets? So the TRAPPIST-1 system is a system of 7 planets, all of which are roughly between the size of Venus and Earth, and they all happen to be. And this particular planetary system is remarkable because there's 7 of them, and there's 3 of them that lie in this habitable zone, E, F, and G. And there's some theories suggesting that even a fourth one might lie in the habitable zone. And this planetary system is situated 40 light years away from Earth, and it orbits, and these planets orbit a star, which is a tiny star whose mass is about 9% that of the sun. And moreover, these planets are all very closely spaced. So the distance between each of these planets is about 100 times smaller than the distance between Earth and Mars. So it's a very different planetary system in some respects compared to the solar system. And then there's been a lot of debate about how life on the TRAPPIST-1 planets could be if it did exist, and how this life would be under a red sun. Because this particular star, which is known as TRAPPIST-1, is what is known as an M dwarf, and these particular stars are red and dim. And so it's believed that in many ways, life on these planets would be quite different from that which we would find on Earth. For instance, the photosynthesis which occurs on Earth in the visible wavelengths might actually occur in the infrared and so on. So this is one of my favorite planetary systems, and I've spent much time thinking about it. And um, the discovery of more and more exoplanets is expected to occur. And for some of these exoplanets, we want to really know if they could be harboring life. And the telescope that would enable us to do so is the James Webb Space Telescope, which is scheduled to be launched either this year or next. And the area of the James Webb Space Telescope is about 7 times that of the Hubble Space Telescope, which is currently operational. So this will provide us a wealth of information about the nature of some of the exoplanets. And then the question is, how do we use the James Webb Space Telescope to look for signs of life? Well, it so happens that when light from the star, let us say TRAPPIST-1, passes through the atmospheres of these planets, what happens is that along the way, depending on whatever molecules exist in the atmosphere, some of these molecules would absorb the light, And as a result, when you look at the spectra, which means you take the light and then you put it through a spectrometer and then you analyze it, you will find that in certain depending on the nature of these molecules, you will see certain dips or peaks in the light that has been obtained. And depending on the nature of these peaks and valleys that one sees, one can infer what types of molecules exist. And in doing so, we can learn a lot about whether these planets are habitable. And in the ideal case, we can also learn a lot about whether these planets are actually have life. And before I move ahead, I should say that the Trappist-1 system is also a fairly recent discovery. It was found in 2017. And the Proxima Centauri b, which is the other one which I mentioned, the exoplanet closest to Earth, was also detected fairly recently because it was found in 2016. And so, as I said, one can use the atmosphere as a window, as a probe into exoplanets, into the nature of these exoplanets. And so, what kind of signatures can we expect to see from afar using these telescopes? And the answer is, well, let's take photosynthesis, for example. Many of you would know that plants and quite a few other organisms, such as cyanobacteria, which are sometimes called blue-green algae, they all take up carbon dioxide from Earth's atmosphere, undertake photosynthesis, and liberate oxygen as as the product. So, if we were to find oxygen in the atmospheres of these worlds, that could be indicative of the presence of life. And that's one type of biosignature that one can hope to look at, where you use the atmosphere as a probe of the given exoplanet. But in certain cases, you can also look at the surface of these exoplanets by looking at the light that is reflected from the surface of these exoplanets. And again, on the surface, if you have um, certain features that absorb strongly at some wavelength and reflect strongly at other wavelengths, again, by using a spectrometer, one can basically infer what kind of substances are there. And there is one substance in particular which is quite remarkable. And that substance is none other than chlorophyll. So, chlorophyll is, of course, the pigment that enables photosynthesis to occur um, in plants and quite a few other organisms, in algae, fungi, and so on. And chlorophyll has this unique property that it absorbs very strongly and it reflects very weakly at wavelengths that are in. It basically absorbs very strongly uh, photons which are in the range of blue to red. But once you cross the red wavelength, it becomes very poor at absorbing light, and therefore its reflectance increases. So instead of absorbing, it reflects most of the light that comes at wavelengths longer than red. So by again looking for this sharp increase in the reflectivity of this chlorophyll around the red wavelengths of light, one can basically infer that chlorophyll is present on the surface. And chlorophyll is an extremely complex molecule that cannot be manufactured through non-biological processes to the best of our knowledge. And therefore, if we were to find a signature that corresponds to that of chlorophyll, it would indicate that we are in a position to claim that we have detected life on that planet. So far, of course, I've talked about trying to detect life on exoplanets by, looking for the analogs of plants or bacteria or fungi, algae, and so on. And then, of course, there is one very special type of life that I haven't commented on so far. And that life is life which can produce very advanced technology similar to human. And this field, of course, is none other than the famous Search for Extraterrestrial Intelligence, SETI, which originated in 1960, and it went through a lot of ups and downs. And in the late 20th century and the early 21st century, it mostly went through a period of down. But now it's seen a revival of sorts with more and more larger surveys coming to the forefront thanks to an increased amount of funding. So SETI, of course, tries to search for signatures of intelligent life. And one of the ways one can do so is by trying to monitor the skies for any kind of radio transmission that might occur. And this is indeed how, SETI has operated for 60 years. But over the past several years, again, there's been a lot of broadening of the types of signatures that could be produced by intelligent life. Earlier, most of the emphasis was on searching for radio signals and in some cases for laser signals. But now we are beginning to look at more and more different types of signatures that could result from intelligent life. This includes searching for city lights that could exist on exoplanets, as you can see here, searching for signatures of industrial pollution that could exist, searching for signatures of satellite belts, and so on. So this is one more avenue where people are trying to look for life elsewhere in the cosmos. So as you can see, there's a multitude of avenues that are open to us, all of which have sprung up in the last decade or so and are continuing apace in the coming decade. So this includes, as we saw, the search for life within our solar system by sending robotic missions, the search for life by using telescopes to look for signatures of microbes and plants and whatnot, and last but not least, searching for signatures of intelligent life. All these avenues have a common name, namely to understand whether there is life elsewhere in the universe. And lastly, we have the thing of where are we going? And I won't spend much time on this. This is also a very important part of astrobiology, obviously. And of course, there's been a lot of interest in the possibility that humans may become a multiplanetary species. So people have been coming up with more and more schemes as to how to make Mars more habitable and what potential human settlements on Mars might look like. So Mars, of course, is the target for most people's speculations and visions and so on. But then there have been a few more radical proposals as well, such as having cloud cities in the atmosphere of Venus, because if you remember, in a certain altitude in the Venusian atmosphere, one could have the right temperatures and pressures which might be conducive for life. So one could think of having permanent floating cities in the clouds. And this is quite similar to one of the worlds in Star Wars. I don't quite remember if it's Bestin or not. I'm sure somebody can update me on that. And so that's some of the habitats that have been discussed. And so eventually over time, there are some ideas that humans might go on to also explore other worlds and perhaps settle on them in the solar system. But if you look at one of the things about astrobiology is it looks at really long time scales. So we already saw evidence of that when we went billions of years back in time to try and understand when the first signatures of life manifest. Now one can also go billions of years ahead in time and ask what could happen then. So the sun, after it runs out of fuel, broadly speaking, will enter what is known as the red giant phase, where it rapidly expands outward and its luminosity increases greatly as well. So in this red giant phase, the sun will grow extremely large and it will either engulf the Earth or come very close to doing so, in either event rendering the Earth uninhabitable. So if we were to look billions of years down the line, if there is some form of intelligence that is left on Earth, it would probably seek to migrate elsewhere. And by elsewhere, I mean even possibly out of the solar system as well. And so, if we want to go interstellar, if we want to travel between the stars, now that may seem like a very lofty goal because the distances between the stars are huge. If we were to take a normal chemical rocket and try to get to the nearest star to Earth, it would take about 100,000 years. which is about one-third the length of time that Homo sapiens has existed on this planet. And so it's a huge number, and therefore it may seem that these distances are too large. But there's technologies that are being pursued even today, and I've also looked into this matter a bit, which aim to develop spacecraft that can travel at a fraction of the speed of light. So if you travel at the speed of light, the journey to the nearest star, which took 100,000 years, would only take about 42 years. And if you therefore travel, say, at 10%, oh, sorry, it would just take 4.2 years. And if you travel at 10% the speed of light, then you would get there in 42 years. So, which is half a human lifetime. So, if one can develop technologies which enable us to travel at what we call relativistic speeds, then even interstellar travel becomes possible. And what we see in this figure is one example of a technology that is being seriously considered from a theoretical standpoint. And that particular technology is known as a light sail. So many of you, would know what a sailboat is. So if you put a sail on a boat, the wind would essentially push the boat ahead. In a similar fashion, light itself has a certain momentum which it can impart to the sail, and and just like a sailboat, one can actually make spacecraft travel at very fast speeds by applying a lot of light onto these spacecraft. So by using large laser arrays, one could actually make spacecraft travel at a fraction of the speed of light. And those particular spacecraft, which rely on photons, namely particles of light, for this particular mode of propulsion, are known as light sails. And laser-driven light sails could, in principle, reach very high velocities, about 10% the speed of light or so. We have already developed some prototypes of light sails, but they're at a very rudimentary stage, and the speeds that we've achieved are only about that of chemical rockets. But again, this field is just beginning to blossom, and we are, there's a lot of unexplored vistas ahead of us. So going interstellar, perhaps. And on that note, let me end with this quote from Carl Sagan. Our remote descendants, safely arrayed on many worlds throughout the solar system and beyond, will be unified by their common heritage, by their regard for their home planet, and by the knowledge that, whatever other life may be, the only humans in all the universe come from Earth. And this is taken from Pale Blue Dot, which he wrote in the 1990s. And that brings my talk to an end. Thank you for listening, and I'll be happy to take questions.
All right, thank you, Dr. Lingam. I hope everybody was able to enjoy that. It was a fantastic talk. One of the things that people mentioned at the beginning was your book. Actually,
Oh,
Library Bill from the library actually mentioned your book that was recently published. So
right.
I have a copy here, and it's called Life in the Cosmos, from biosignatures to technosignatures. So do you want to say a little bit about your book and kind of what more can people learn from your book that maybe they can
Yeah,
get a taste of here in this talk?
yeah, absolutely. I'd be happy to. Just that I didn't want to toot my own horn, but thank you. So this book is written for what I would say mostly an audience of undergraduates with a strong background in the sciences. It can be typically the physical sciences, but not necessarily, but also graduate students as well. And this book aimed to, in a sense, it is ideally, it would I see it as the successor to a very important book that came out in the 1960s, which was the book by Joseph Klowski and Carl Sagan called Intelligent Life in the Universe. So what this book tries to do is to precisely look at the three questions that we talked about. So first being, how did life originate on our planet and on other worlds as well? And some of the first 2, 3 chapters focus on that. And then the bulk of the book examines what does habitability mean, what are the various habitable worlds, and what are the conditions needed for habitability, and last, of course, how could we detect signatures of non-technological life, which are known as biosignatures, so signatures of biology. And the last chapters focus on the search for intelligent life, which, as I mentioned, has been rather marginalized. And this looks at some of the history of the field, some of the new methods that have come up, as well as some of the future ahead of us. And lastly, it also discusses how we can undertake space exploration both within our solar system and beyond by deploying state-of-the-art technologies that go beyond chemicals rockets. It's a big book. I believe the library has one or two copies, so you're all welcome to look at it. And yeah, if you happen to be interested and you would like to get a copy, of course, I would be happy as well. Thank you.
All right, thanks. So we have several audience questions. And before we get into them, I just want to repeat again, thank you guys for your patience. Thank you for being here. Apologies for the technical difficulties. So lesson learned, always have a backup computer. So glad we could be here today. All right, so our first question or sets of questions are from Brian Murphy. And this is regarding Venus, and he's asking, are you looking forward to the potential new data from NASA's Veritas and Da Vinci missions? And could these missions advance astrobiology on Venus? And this was when you were talking about
Um,
your phosphine detections.
mhm.
So.
Yep. Yeah, great question. Obviously, I'm looking forward to seeing what comes of it. And I'm very glad that Venus has finally gotten its attention that it deserved. It has been one of the most neglected targets in the solar system. And here, I don't even mean astrobiological targets, just been very scarcely explored, especially by the European Union and by the US. There were some Soviet missions in the past. And yes, I think we will learn quite a bit about the habitability of the Venusian clouds and of its atmosphere. But I would say that these two missions are not astrobiological missions as such, because at least as of now, the payload is not planned to have any explicit detection instrument that I'm aware of. It does, however, aim to characterize the atmosphere of Venus in the broad sense and to learn more about its properties. But I don't think there's much dedicated instrumentation towards that end. Now, of course, I might be wrong, or the plans might eventually change. So, yeah, I think certainly, any kind of data would be welcome because we have so little. Yeah.
Great. So next we have a comment from Jordan Holseth that she or he is glad that you started talking about Titan because one of their favorite bodies in the solar system. And so that brings us to Brian's question as to what are your thoughts on the future Dragonfly mission to Titan? Or do you have any
Yeah.
thoughts? Yeah.
No, I think Dragonfly is, I mean, obviously it's super cool. And I was a bit concerned that maybe Titan would be put on the back burner because, Cassini Huygens is not that many years back. And indeed, there was proposals for a future mission to Enceladus, which is also one of my favorite worlds, but that was shelved because people argued, well, it had its moment in the sun and so on. So yeah, I'm glad that we are seeing a mission to Titan. I think Titan and Venus, for different reasons, are not conventional astrobiological targets because um, they don't really harbor water on the surface. Venus may have an aerial biosphere. Titan may have a surface biosphere, but it would be quite different from that which we know on Earth. And some of the objectives of Dragonfly do indeed, strongly overlap with astrobiology, and I do expect fairly dedicated instrumentation to be there as well. So yeah, I think Dragonfly will be really interesting to see. Of course, the the day when we get concrete data from it is quite far away because it's about 15 years in the future. But as they say, say, the longer you wait, the sweeter the success will be. So I suppose in that sense, it'll be even more nice to see what comes of it.
So is it 15 years till launch or 15 years until it arrives to Titan? Because
Yeah, 15 years until I mean, roughly 15, maybe 14 or 13 or so. So it'll launch allegedly at the end of 2027, and it would take about 8, 9 years to get there. So it's not something that is there in the near future. But that's sort of why I believe I'm sort of going a little bit off track, not too much, but that we should be considering more use of miniaturized spacecraft. Obviously, they're not going to have um, the same degree of exploration potential as larger missions do, but then the science return would scale with the number of such small spacecraft that one sends out, and it would scale in a super linear fashion. So if you 10 small probes for the same amount as one large probe, I do believe that you can have more versatility and potentially more data as well. And the two can be done in tandem. It's not just one or the other. So as I said, this is a little off topic, but I think it does relate to some of the things that I talked about, as well as some of the questions that came up.
all right, our next question is from Turbo Cayman. How do you, or what do you think the probability of a successful permanent Mars colony is given that the gravity is 1/3 that of Earth?
Yeah, there's a lot of challenges for Mars. I mean, one is certainly gravity. The other, of course, is the atmosphere is just too tenuous. So we would have to find we would either have to build very localized cities or some kind of domed encasements where you have habitat, or you would have to find a way to raise the surface pressure of Venus altogether. So there's gravity, there's temperature, and again, if you're on the surface, there's all this radiation that is extremely dangerous. So in which case you would need shielding and so on. So it's definitely not going to be easy. But that said, there are caves and certain habitats which are more conducive, things called lava tubes and so on, where potentially one could have this. And even if not a whole, a planet spanning settlement, one could still think of isolated settlements that one could have. And people have shown that you can make localized greenhouse effects happen very effectively without too many resources. So you could raise the temperature to a fairly conducive value for humans as well. And gravity, of course, we can't do a whole lot about that. And there's still a lot that is not very well understood about what would happen about the long-term effects of gravity over multiple generations. We do have data from the International Space Station, but that's only for a few years at most, and not several decades continuously. So I think it's a good question, a lot of unknowns, and yeah, it's a very promising field to think about.
I mean, also conversely, like were mentioning the cloud cities in Venus, which you were
Right.
right, it is best spin according to Ryan. Um,
Okay. Yeah.
I mean, that also has even a lot more challenges because, yeah, you talked about
Right.
pressure and
Yeah.
temperature, but the atmosphere composition is also
Yeah. Yeah.
pretty
There's no
toxic.
oxygen at all. Indeed, absolutely.
Yeah.
There's zilch. I mean, there's no oxygen. Yeah, no, it's not that it's any easier, and that's why I said it's actually a more niche proposal because that would be harder in a sense than Venus. And in fact, there's another quote from Sagan from the same book where he says that in the short term, the Earth is really the best place that we have for human settlement, and that's why we should take care of our planet. So I did think about putting that quote in. There wasn't the right occasion didn't come up. So yeah, all these other worlds do have a lot of problems compared to Earth, which is not surprising given that we evolved on this planet. We are well adapted to live on this planet, and we definitely are not so well adapted to live on these other worlds.
Yeah. Then we have one more question. So if anybody else has any more questions, please include them in the chat. and we'll ask Dr. Lingam. So we have another question from BA. So you showed that there's a lower limit for cell size. Is there an upper limit as to how large a cell can be?
That's a great question. So even the lower limit is not super strict. It's set by a number of different things. So there's what one could call information factors, which I discussed. There's also the fact that if you want a functioning cell, you need to have a certain array of biomolecules, such as a minimum inventory of proteins, a minimum inventory of nucleic acid content, and so on. So the fact that you need to have a minimal stock of biomolecules also imposes a lower limit. Now, coming to the upper limit, people generally believe that the upper limit is set by diffusion because cells acquire a lot of substances through diffusion. So, if the cell is very large, it would take a lot of time for the appropriate molecules to diffuse from the boundary of the cell to the interior. And in that time, the cell may already have lived out its lifetime. So diffusion is generally considered to be the upper bound for the cell, but note that I use the word generally considered to be because, again, there's a lot of debate about this point and also a lot of uncertainty because there are certainly other mechanisms such as advection which could work instead of diffusion and enable the same outcome to be effectuated. So overall, I would say that that's a really good question. It's not again, it's not fully settled, but people do think that at least for prokaryotes, that is namely bacteria and archaea, the upper limit is in a few microns or so. When you get to eukaryotic cells, then they have more sophisticated transport processes, which can make them larger. So all in all, it's not a fully settled question, and it's a very good question.
Okay. As far as I can see, this appears to be all the questions we have so far. So I want to thank you, Dr. Lingam, again for a fantastic talk. Very informative. And again, if you guys are interested, the book is called Life in the Cosmos. If you want to learn more. And thank you all for your patience and for sticking with us and your loyalty. We will be back next month with Dr. Bachelor, for those of you that remember him. And yeah, I'm giving you a virtual applause to you from our audience. So see you guys next time.
Right. Thank you.